Okay, so acceleration is something you went over in Science 10. Okay, so we're kind of gonna just quickly review what acceleration is. In Science 10, that's kind of where you stopped. Okay, you learned that acceleration was a change in velocity over time, and then you learned the one acceleration formula we teach you in Science 10. You learned how to manipulate it, and that was kind of it. Okay, today we're going to go over probably that far, and maybe we'll get to one of the other 4 acceleration formulas that you're going to be using. I have 5 in total, the one you learned from last year and 4 others, okay, that can be used to solve acceleration problems. Right, so that's what we'll be looking at here over the next day and a half or so. Okay, so first off, what is accelerated motion? Well, accelerated motion is a change in velocity over time. Okay, and that's again where you got this formula that you learned last year, okay, VF minus VI over T. That's where you got that from. Change in velocity over change in time. Okay, where does that formula come from? Well, it comes from a velocity versus time graph of an accelerating object. Okay, it is the, what part of that graph? It's the slope. Okay, because remember, it's change in velocity, which is the change in y over the change in time. Okay, that's acceleration on that graph. That's where that formula comes from. Okay, we learned that back when we did graphing, but that's where that one comes from. But that's only going to relate acceleration, velocity, and time. We're also going to have some formulas that will bring displacement in as well. Okay, so look at how far the object goes while it's accelerating, okay, and that'll be part of it as well. So that's where number 2 comes in here. Learn the relationship between change in velocity, distance, time, and acceleration, and then obviously be able to solve problems related to acceleration. Okay. All right. So whenever the velocity of an object is changing, then we say the object is accelerating. Okay, the meaning of average acceleration is best, okay, or uniform acceleration is best exemplified by a plane taking off. Okay, why is a car accelerating away from a stoplight not a good example of uniform acceleration? Because it's not uniform. Yeah, what does your car have that change all the time while you're accelerating?
Gears.
Gears, right. Okay, the reason your car has gears is because it can't just have one gear, okay, or it would over-rev the engine by the time you got to highway speed. Or it wouldn't over-rev the engine at highway speed, but would be absolutely gutless, okay, when trying to move away from a stoplight, right? If you've ever driven a Standard, okay, this is silly, but how many of you have actually driven a Standard before? Okay, that's more than I thought. Okay, you ever try to start in like third?
Yes.
It's nearly impossible. Okay, because the ratio of the gears just doesn't work. Okay, trying to start in third. Okay, so your car switches gears to give you the best acceleration at different speeds. But what that means is your graph of your car accelerating is not a diagonal line. It's actually a flattening curve. Okay, because as you change gears, your car's rate of acceleration decreases. Your car's best acceleration is in first, and then in second, and then third, and then fourth. Okay, it gets less and less and less, and maybe you have a 10-speed transmission that sounds more like a bike than a car, but that's what we're going towards. Okay, so the higher the gear, the less the acceleration you have. Okay, which is why in most cars that have automatic transmissions, when you try to pass somebody, what does your car do when you floor the gas? It changes gears, right? It jumps down a couple of gears to give you better acceleration. If you've driven a Standard, you know how important this is. You don't just pull out into the passing lane in sixth, because you'll die, okay? Because your car will just go and not accelerate, and the oncoming car will get you. Okay? You definitely gear down into maybe fourth or even third, okay, if you want a little extra jam to get around that car. Okay, and it automatically does that for you. Okay. All right, so a plane is better because a plane doesn't have gears. It simply rotates the engines faster and faster and faster, okay, producing thrust that actually gives it a pretty linear rate of acceleration until it starts using the wings for lift, and then of course it slows down a little bit. But as it's accelerating along the runway, it's much more linear than a car's acceleration is. Okay, so this is the formula we're familiar with, okay? That acceleration is the change in velocity divided by time, okay? We learned how to manipulate that last year, okay? Rules of algebra, all of that, okay? But there's, like I say, other formulas that we're going to be going over. Okay, so really what we need to get off of this slide is that acceleration is change in velocity over time. Okay, so in an easy example here, like you would have learned in Science 10, okay, if we've got this plane and it starts from rest, okay, and anytime something starts from rest, VI is 0. If it comes to rest, VF is 0. Okay, so rest always means it's stopped. Okay, so it's at rest at time 0. The plane accelerates down the runway and 29 seconds later is moving at 72.2 meters per second in a forward direction. Okay, we want to find the average acceleration of the plane. All right, so acceleration is change in velocity, VF minus VI over t. Okay, we're told the final velocity was 72.2. Okay, subtract the initial, which was 0, divided by the time, which was 29 seconds. Okay, so when we do that, okay, we'll have 72.2 divided by 29 seconds. Okay, and we're looking at an acceleration of 2.5 meters per second squared. All right, why are our units meters per second squared?
Because it's meters per second, they just mean second.
Right, it's meters per second, okay? And so when you're looking at units, okay, meters per second divided by seconds, okay, or meters per second, when you divide fractions, what do you do with the second one? Right, you flip it and then you multiply, right? So what you end up with is meters over seconds times 1 over seconds. Meters times 1, meters. Seconds times seconds, seconds squared. Okay, it doesn't mean your number is squared. It doesn't mean you need to square root anything, because I see people do that. Don't do that. Okay, it's just the units. It's meters per second. Okay, is that ringing a bell for everybody? All right. Okay, so that's what the calculation we just did, 2.5 meters per second squared. These are your other 4 acceleration formulas. You need not write them down as they are on your formula sheet. Okay, so we've got a whole bunch here that all involve displacement. Okay, we only have the one that was from before, okay, that doesn't have displacement in it. All these other ones involve displacement as well. Okay, so I'm going to kind of briefly talk about where they come from and kind of how they work and how often you might use them. Okay, these two we'll use quite a bit. Okay, and they come from, again, a velocity versus time graph. Okay, so if I have a velocity versus time graph of an accelerating object, how do I get displacement from that graph? It's the area under the line. Okay? Now, that formula, the first one, is supposed to calculate displacement, which is the equivalent of the area underneath this line. So, the area underneath this line consists of a rectangle and a triangle. Everyone okay with that? Okay. So right here, at time 0, this object is actually moving because its velocity isn't 0. So this would be its VI. Right, this would be its initial velocity. Okay, the base of the triangle would be the time. Okay, so look at what we're calculating here. The first part says VI times t. Well, VI times t is calculating the area of that rectangle, is it not? It's base times height. All right, and then there's this 1/2 AT squared. That's actually calculating the area of this triangle. All right, it's 1/2 of essentially the base times the height, but it's written differently. Okay, it's time squared times acceleration. It's still calculating the same thing, okay, but it's calculating the area of this triangle. Everybody okay with that? Okay, this one does exactly the same thing, but it uses the final velocity instead. So it's going to go up here, okay, and use VF. So VF times T calculates this whole box, okay, everything in this box. And then it subtracts that triangle, still calculating the area under the line. Okay, one is the one you use if you have VF and not VI, and this is the one you use if you have VI and not VF. Okay, but they calculate the same thing. They're calculating the area under the line. Okay. Now, the next formula is not really a graphically derived formula, okay, but it is going to calculate either acceleration, either the two velocities, or displacement without what? Without time. Okay, so this one comes in pretty handy if you don't know the time. And it's especially handy when we're doing projectile motion, which is the last thing in this unit. We use that one a fair amount when we're trying to calculate the maximum height that a projectile will reach, because we don't know what time that occurs at. Okay, so it can be pretty useful in that regard. Okay, and then our last formula here, okay, calculates again displacement by taking VF, adding it to VI, and dividing by 2. What does that sound like calculating? An average, right. Okay, it's calculating average velocity and then multiplying by time. So really, this is just V times T. We don't use that one very often because it makes some assumptions. Okay, these other formulas will work whether the acceleration is uniform or not. This one won't. Okay, the acceleration has to be uniform for this one to work. Okay, and so anytime you see a question that says assume uniform acceleration, or this object accelerates uniformly, it makes kind of a big deal out of the uniform part, it's probably referring to this one. Okay, this is the one we'll probably use the least. Okay, just we don't use it that often. All right, and the reason we don't use it that often is, can you use this formula if you're calculating something about an accelerating object? Not really, because what is it assuming the velocity is not doing? Right. It's assuming a constant velocity. So when it does this, it's using the average velocity, which, like we said, is only really true if it's perfectly uniform. Okay. All right. So we're going to go over a few examples here, basically one or two examples for each formula. Okay, so we kind of get the hang of how to use each one of the formulas that are going to be involved, look at the manipulations for each formula, and that kind of thing. Okay, so that's where we're headed here now. All right, so our first example here is we've got a hybrid car with an initial velocity of 10 meters per second east. All right, so they just gave me VI, 10.0 meters per second east. It accelerates at 3.0 meters per second squared. East. Okay, how long will it take the car to acquire a final velocity of 25 meters per second east? Okay, how long means I'm looking for what? Time. Okay, here's why it's important to write down your givens. Okay, if you don't have your givens written down, it's harder to choose the right formula. Remember, you've got 5 acceleration formulas on your formula sheet. Writing down your givens, okay, helps you to decide which formula is going to be best for you given what you have. Okay, which formula should I use with these things? Okay. I don't have displacement, and I'm not asked for it. Can I use any of the 4 formulas we just looked at? No, because they all have displacement in them. So for this one, I need to use the change in velocity over time equals acceleration, the one from last year. Okay, because it's the only formula that has the 3 things I have and the thing I'm looking for. All right, so I've got acceleration equals VF minus VI over t, and I'm trying to solve for t. Okay, so if I want to get t by itself, what should I do? Multiply it over to the other side. I can't solve for it when it's on the bottom of an equation. So I'm going to multiply it over to this side. What am I going to do with a? Right. Okay, so there's my formula. T equals VF minus VI over a. Okay, so that'll be 25 minus 10 over 3. Okay, so 15 over 3, this should take 5.0 seconds. Everybody okay with that one? All right, let's maybe quickly look at the different manipulations of this formula here. All right, so we just looked at how to manipulate this for t. How would I manipulate this for VF?
You times the left side A by T, and then
Okay.
plus VI.
And then I would add VI, exactly. Okay, so I move what's not attached first, okay, and then I do my other operations. So that'll get me VF, okay? And this should make sense. If I'm looking at this, T times A equals VF minus VI. That's the change in velocity, right? So T times A equals the change. If I want to find the final, I should add whatever I started with to the change to get me the final. Okay? And it would work the opposite way if I was looking for VF. I should take the change and, or I should take, sorry, sorry, if I'm looking for VI, sorry, I said that wrong. If I'm looking for VI, I should take the final and subtract the change, right? If I take the final, subtract how much I changed it by, that should give me VI. So if I was looking for VI, it would be VF minus T times A. Okay, those are our manipulations. All right, I want you guys to try these two. They both involve using that formula. Okay, answers are down below, so you can check and see if you did them right or not. Okay, but that's the ones I want you working on right there. Give you a couple minutes and we'll look at them together. Okay, so for number 2, okay, we have our initial velocity, okay, of 20 kilometers per hour, okay, and we're going to divide that by 3.6 to get our meters per second. Okay, so 5.5 repeating meters per second, and that's north. Okay, it accelerates at 1.5 meters per second squared north. Okay, and it does that for 9.3 seconds. Okay, we're looking for its final velocity. Okay, so A equals VF minus VI over T. So we multiply both sides by T and add VI in order to get VF. So that'll be 5.5. Excuse me, 5.5 repeating. Okay, plus 9.3 times 1.5. Okay, and when we do that, we're going to get an answer in meters per second. Okay, so plus 9.3 times 1.5. Okay, so we get 19.5 meters per second. Multiply that by 3.6, okay, and you've got your kilometers per hour, 70 kilometers per hour. Okay, I'm never going to make you do that. Okay, on a question, because I really don't care about metric conversions very much. Okay, now I might have you convert like kilometers to meters, but not a compound conversion. Okay, on a test anyway. Okay, any questions on those two? All right, then let's have a look at the next formula. Okay, so write this example down because this will be our next formula. I've got a cattle train being brought to traveling west at 16 meters per second. So they gave me VI, 16.0 meters per second west. Okay, it's brought to rest. So what's VF? 0. Okay, find the displacement of the cattle train. Okay, while it is coming to a stop. Okay, it takes 8.0 seconds for it to come to a stop, and then it uses this. Assume uniform acceleration. All right, so first I've got that big hint that we talked about already. And secondly, I have VI, VF, and T, and I'm looking for D. All right, the only formula I have that fits that bill is this one. D equals VF plus VI over 2 times T. All right, and in this one, I am looking for the displacement. So I don't even have to manipulate it. I just need to plug in my numbers. It's already set up for D. Okay, so that'll be VF, which was 0, plus our initial, which was 16, divided by 2, okay, times 8 seconds. All right, well, 16 over 2 is 8, okay, times 8 is 64 meters, okay, and that'll be west. all right with that one? All right, let's look at manipulations of that formula just so we know what we're going to be doing. So I've got D equals VF plus VI over 2, and that's all in brackets, times T. So if I want to find T, what do I have to do?
Divide the entire bracket by.
Yeah, exactly. Okay, think about order of operations. I would do whatever's in brackets before I multiplied by T. So what's in brackets is really just one number. Okay, so this is one number, X times T. Okay, if I want to find T, I just divide both sides by this whole bracketed thing. So I'd have D over VF plus VI over 2. Okay, that would equal T. Now, if I wanted to find either one of the speeds, right, what do I have to move first? T. So I'm going to divide both sides by T. Okay, so this should make sense. D over T equals average velocity, right? Okay, so let's say I want to find VF. Doesn't matter, VI or VF, same manipulation. Okay, what do I have to do with the 2? Okay, multiply it. Okay, so okay, and then I would subtract VI. Okay, if I wanted to find, so I'll subtract VI over here. So I have 2 times D over T minus VI equals VF. Everybody all right with that? Yeah. Okay. If I want to find VI, what do I do with VF? Same thing. Subtract it over. Okay. Everybody all right with that? All right. Let's have you try those two. They involve that formula. So in the first one, we got a hound running at a velocity of 16 meters per second south. So that's going to be our VI. South. Okay. And slows down uniformly to a velocity of 4 meters per second south. Okay. What's the displacement? Sorry, and that takes 4 seconds. What's the displacement during this time? So that doesn't require any manipulation. It's just VF plus VI over 2 times T. Okay, so that's going to be 16 plus 4. Okay, over 2. Okay, and then multiplied by 4. So 16 plus 4 is 20. Over 2 is 10. Times 4 is 40. Okay, so we got 40 meters south. Okay, and then the trick with number 2, guys, is you have to get the directions right on question number 2. Initially, the ball is rolling up the hill with a velocity of 3 meters per second uphill. Okay, 4 seconds later, okay, it's moving down the hill at 9 meters per second. So that's got to be negative compared to the other. Okay, I will post tomorrow, or some questions like tomorrow's quiz. Okay, at the end of the day, it'll be vector addition. All right, so be ready for that one.
Hey, this dial is